All right. So today we'll be wrapping up our talk about nonlinear material behavior in the context of finite element methods. And I thought I'd conclude that sequence of lectures that we've been, pursuing on this subject by providing you with some description of how exactly nonlinear material behavior, and more specifically, elastoplastic material behavior, how does that fit into this context of a finite element analysis as we have described in the first half of the class, and partly in our discussion of, formulating nonlinear finite element methods. So that's the goal, is to give you a sense of how these constitutive models or material models would actually be implemented in some finite element code, and how they would actually go about enforcing some of the conditions on, plastic strain evolution and, elastoplastic stress update procedures. How exactly do all the equations that we've been talking about over the past couple of lectures, how do they fit together? And so I'll give you some specific examples of common so-called elastic-predictor, plastic-corrector algorithms that are implemented in a lot of different finite element codes that deal with elastoplastic material behavior. And you'll have an opportunity to maybe even program such an algorithm yourself in the context of this extra credit assignment. Sounds daunting, but it's actually remarkably simple, as I hope you'll see momentarily. But before we dive into some of those details, I wanted to provide a brief recap on what we talked about last time in the context of continuum formulations of elastoplastic material models. And just to provide you with the high level of what were the key things of interest that we're going to talk about and continue to discuss in today's lecture. We talked in last lecture about how we went about generalizing our condition for when plasticity occurs. We had to define some yield criterion. When the stress reaches some critical limit, that's when we say plasticity occurs. And that was straightforward to define in a uniaxial stress strain context, but in this multiaxial stress context, we had to come up with some new measure of stress, which we used to assess this kind of, criterion for failure. And that particular measure of stress was the von Mises measure of stress. It was effectively this sigma with a bar over it, which is in effect a measure of, the magnitude of shear stress in the material. It also has a nice geometric interpretation if we were to go about displaying states of stress within some principal stress coordinate system, kind of an interesting idea. But if you had some state of stress, which you could represent in terms of its three principal stresses, and if you could display that state of stress as a point within this kind of three-dimensional principal stress space, then we found that that state of stress could be further decomposed into a part that involves just pure hydrostatic pressure, and such states of stress would lie along this hydrostatic stress axis. And also, you could decompose a state of stress into, its purely deviatoric part, S, characterizing just the shearing part of the total stress. And we determined that if we wanted to come up with some criterion for plastic strain evolution, really based on experimental evidence and other kinds of material science principles, we rationalized that, especially for, materials like metals and things like that, it's really only the shearing stress, the deviatoric stress, which influences plastic strain evolution, and also which is governed by some constraint on, the maximum stress prior to which yielding occurs. So we came up with this kind of yield criterion expressed as what I'll call a yield function, this f sub y, which is really just, this effective measure of stress, the von Mises stress, minus the yield stress. And if this yield function happens to be less than zero, it implies that whatever state of stress that we have, which is kind of measured by this kind of von Mises stress, if this state of stress lies inside of this corresponding, cylinder that exists in principal stress space, whose radius is directly proportional to the yield stress of the material, as long as we're inside of that cylinder, then we have purely elastic behavior. We don't meet this yield criterion. But as soon as the yield function is equal to zero, it means that our state of stress lies directly on this yield surface, and that's when we have actual plastic deformations occurring in the material. At that point, we also had to come up with some description of what exactly governs the change in the plastic strain in the material in order to enforce this constraint continuously. So as plastic flow is happening, as plastic strains are evolving during plasticity, we have to insist that this constraint is always satisfied. Either we're inside the yield surface, in which case we don't have to do anything, the material is behaving strictly elastically, and we assume that no plastic strains are evolving at all. So we can kind of proceed as normal. However, if, let's say, we are kind of at the point of yielding, we're kind of like out on the yield surface, we have to enforce this condition continuously, and we have to say that this yield function is equal to 0. Or in other words, the effective or von Mises stress in the material has to be directly equal to the yield stress during active plastic loading. And to enforce that constraint, we have to change the plastic strain in the material. And we can't just change it willy-nilly. We can't just, randomly decide, well, let's update the plastic strain, but, maybe increase it in some arbitrary direction of loading that may or may not be aligned with the actual applied loading to the structure or chunk of material that we're looking at. We actually had to insist that the direction in which the plastic strain changed or increased had to be directly proportional to the state of deviatoric stress in the material. Another way of intuiting that, at least in the one-dimensional context, is to say that if we're loading some kind of uniaxial bar in tension, it implies that the plastic strain has to increase corresponding to elongation. And conversely, if we had, uniaxial compression, it would mean that the plastic strain has to decrease corresponding to uniaxial compression. Right. Okay. So from these criteria, we established that this direction in which the plastic strain evolves has to be directly aligned with this, deviatoric stress in the material, which, as it happens, can be represented as basically just this normal to this yield surface. Which is kind of interesting. You can compute this normal as basically just the derivative of the yield function with respect to the total stress, which is kind of an interesting way of deriving it. Or you can just equivalently take 3/2 of the deviatoric stress normalized by the von Mises stress, and you get back exactly that same quantity. And we also found that we had to come up with some description of an equivalent plastic strain, which was kind of a measure of the total kind of like scalar measure of plastic strain that occurred in the material. And this equivalent plastic strain was a quantity that was always increasing. It was, independent of the direction of plastic loading or anything like that. It was just this kind of single scalar number that's always increasing. It might influence how the yield surface or this kind of yield stress actually changes. And that could lead to behaviors like isotropic hardening and things like that. But in general, we could relate the total rate of plastic strain, the tensor, to this corresponding rate of equivalent plastic strain by noting this association with the plastic flow direction n. Okay, so that's kind of like a long-winded recap of some of those details. But I wanted to kind of present that partly so that you had some context and background to understand the distinction between these two different binary conditions that we might have going on when we're trying to update this internal state of the material, and more specifically, when we're trying to update the internal kind of plastic strain in some chunk of material. So really, there are two situations that can arise when we're loading some piece of material in ideally some kind of incremental or stepwise fashion. But really, it boils down to just these two scenarios. Either we are inside of the yield surface. In a uniaxial stress strain context, the yield surface is really nothing more than these kind of pair of dashed lines, if you like. Certainly, the axial stress can't exceed some maximum sigma y naught value, and it can't go below some lower bound on sigma y naught. So effectively, in this one-dimensional context, we just have these two bounds denoting our yield surface. And as long as we're in between those two bounds, we lie in the so-called elastic range of the material. And within this elastic range, you can verify that the yield function, that Fy function, is less than 0. It basically means that the material is behaving in a purely elastic fashion, and there's no change in the internal plastic strain of the material. So if we were to try to load the material and unload it, it would unload or load along a slope that's directly proportional to the Young's modulus of the material. However, if we load it up to the point where it hits one of these two bounds, in other words, if we go up to the point where this yield function is directly equal to 0, indicating that we're kind of directly meeting this yield criterion, that's when we have to actively update the plastic strain. So really, when I say that we're inside the yield surface, or in other words, when Fy is less than 0, I say that no plastic strain occurs, which is equivalent to saying that the time rate of the plastic strain, or if you like, the time rate of the equivalent plastic strain, that has to be equal to 0. And conversely, if we have plastic loading, then we say that Fy is directly equal to 0 the whole time while it's actively loading under these plastic loading conditions. But in order to satisfy this condition, we have to require that the plastic strain increases, and more specifically, the equivalent plastic strain variable increases at a rate that guarantees that this maintains, equivalence, that Fy is always equal to 0. It's never possible to actually exceed this criterion. You can't go Fy is greater than 0. That is strictly disallowed. At least the goal of our algorithms that we develop is to always try to maintain this. However, as we'll see, sometimes it's convenient to relax that constraint, if only momentarily. So the idea is these are kind of exclusive conditions. Either Fy is equal to 0 and plastic strain is increasing, or Fy is less than 0 and there's no rate of plastic strain. So two different kind of conditions, and collectively these conditions are referred to as the loading-unloading conditions. If you like, there's some mathematical terminology that refers to this collection of conditions, including actually this one, that says that if you multiply these two things together, Fy and the time rate of the equivalent plastic strain, that their product always has to be equal to 0, which is equivalent to saying that if Fy is equal to 0, then, certainly this could be equal to some non-zero value. But certainly Fy and E bar dot P, those two things can't be non-zero at the same time. So one of these two things has to be equal to 0. But if one of them is 0, then the other one could potentially be non-zero. It's kind of another way to interpret this as, again, enforcing these as mutually exclusive conditions. Okay, so collectively, these are sometimes referred to in the mathematical context as Karush-Kuhn-Tucker conditions, which are really conditions that enforce this sort of inequality constraint, sort of a fairly general interpretation of how inequality constraints are enforced in general. And in fact, it actually has some bearing in contact mechanics, as we might get to later on in the course. Okay, so just to wrap up, all of the equations that we've established up to this point give us some relationship between stress and strain in the material, which additionally depends on the total plastic strain in the material. We came up with this yield function, which we said always had to be either less than or equal to 0. Less than 0 implies we're in the elastic range and there's no plasticity. If it's equal to 0, then we have active plastic flow. And those two things are mutually exclusive. That's the loading-unloading conditions. And then finally, we have our flow rule. If plasticity is happening, then we have to have a way of determining how exactly plastic strain should be updated based on, the determination of this kind of equivalent plastic strain variable. And in an incremental algorithmic context, we're not really talking about time rates of these quantities. Usually we're talking more about increments or changes in these quantities. So wherever you see quantities with this kind of dotted symbol indicating a time rate, in an algorithmic context, it would be more like a delta or a delta, EP to represent the change in plastic strain over a given load step. Okay, so these are the equations ultimately that we have to solve in order to update the internal state of stress in the material given some new state of strain in the material. And also, how do we go about updating the plastic strain? That's the other variable that we have to update every time we kind of call our material model. So we have to find a way of algorithmically implementing these equations and solving them such that we satisfy the loading and unloading conditions, the yield constraint function, and such that we satisfy this flow rule condition. So that's the goal. We have to somehow synthesize these things. And I want to remind you that at least in this kind of algorithmic context, if we're updating the internal state of the material, really we're doing that in this incremental fashion. So we're updating the state of stress in the material given some incoming increment in the strain in the material. So maybe the state of stress in the material and the state of strain in the material at some prior time, Tn-1, let's say, is known. And at the next time, Tn, we're given some guess of what we think the displacements are in the problem, which gives us some new guess for what the current or updated state of strain is in this chunk of material. So we have this new driven increment of strain, delta, epsilon sub n, and somehow, given the old state of stress and also the other variables that we have pertinent to the material, the plastic strain and possibly also the equivalent plastic strain, somehow we want to take this delta epsilon sub n, the old stress and all those old history variables, and we want to update them to the new state at Tn. So we need to determine sigma n and the new updated values of plastic strain and equivalent plastic strain. So how do we do that? Well, it turns out it's actually remarkably simple. In the one-dimensional context, I think it's fairly easy to interpret. But the idea is you start with, again, all of these old quantities defined at the previous time step or load step at n-1. Okay, so presuming you have the old strain at time n-1, the old plastic strain at n-1, and from that you can determine what's the old state of stress in the material. You can even determine what's the old yield stress in the material, just so you kind of have that for reference. But really, the procedure for updating the stress, given some new increment in strain, proceeds first by actually assuming that the material behaves strictly elastically. You ignore this constraint that we have to lie inside of this yield surface. We actually violate that condition, but only momentarily. So really the first step in this procedure, a two-step procedure in general, starts by just saying, well, forget about plasticity. Let's just assume purely elastic behavior. And let's assume that it's elastic behavior that's nonetheless shifted by this value of plastic strain, the thing that we had from the previous time step. We have to update it, but we'll figure out how to do that later. First, let's just figure out, okay, apply this increment of strain, which basically gives us some new trial value of the stress in the material, which we can compute just by taking the Young's modulus times the elastic part of the strain. Or in other words, the total strain minus the plastic strain. Okay, now we know that this doesn't necessarily satisfy our yield constraint because clearly you can see we're outside of this bound. We're violating that yield criterion. So the material should be yielding. We noticed this at least. But if we had taken a smaller step that had still left us inside of this yield bound, then it would have been totally fine. And in fact, that's exactly how these algorithms proceed. If we had done this kind of initial guess, assuming strictly elastic behavior, and if we'd stayed inside of this yield bound, then we would have said, we're done. Okay, well, no plasticity occurred. We just had strictly elastic behavior. There's nothing else that I need to do to update the state of the material. Just carry over the old values of plastic strain and treat those as the new values of plastic strain at time Tn. And we're done. That would be really easy. However, when you notice that, in these kinds of scenarios, if you violate the yield constraint, now you have to go back and make a correction. And that's kind of where the terminology of this classical elastic-predictor, plastic-corrector kind of two-step algorithm comes from. It starts by doing this trial elastic predictor step, assuming no plasticity occurs, and then it comes after the fact and tries to correct the error that we've made in violating this yield constraint. So how do we do that corrector step? That's the question. And it turns out it's not so difficult, but the one thing that I want to point out here is that during this initial elastic predictor step, we assume that the total strain in the material increases by some finite amount this delta epsilon sub n. And at the same time, we assume that the plastic strain in the material remains fixed. It doesn't change. It stays the same value that it was from the previous time step. Now, in the subsequent plastic corrector step, we assume the opposite. We actually say during the corrector step, we've already updated the total strain, so just freeze it, keep it as it is. Don't actually increment the total strain. Keep it held fixed at epsilon sub n, because we've already gone up to here, right? The only thing that we're going to change during the corrector step is the plastic strain. So it's kind of like what you're doing in this two-step procedure is first, update the state of the material, assuming elastic behavior by only incrementing the total strain, and then come back during my corrector step and update the plastic strain, holding the total strain fixed. And that's precisely how this kind of second step proceeds. Hold the total strain fixed, but somehow update the plastic strain in the material so that I basically kind of reduce the total stress in the material until eventually I satisfy my yield constraint. If I happen to go outside of the yield bounds, I have to basically advance or decrease, or depending on the direction of plastic flow, which you would have to determine based on your flow rule, you would update this kind of plastic strain by whatever increment so that exactly you satisfy the yield criterion, Fy equals 0. Now, at the same time as you might be trying to increase this kind of value of plastic strain, and in effect, you would be kind of traversing down this kind of vertical graph because you're holding the total strain fixed, it would look like you're basically just traversing downwards. As you're kind of advancing this way, the total stress is being reduced. At the same time, however, if you have some dependence of the yield stress on the total plastic strain in the material, it's possible that, as you might have an isotropic hardening, this kind of yield bound might be increasing, which would indicate that, technically speaking, at the same time as you're trying to kind of reduce the total stress in the material by advancing plastic strain, at the same time, the yield stress might be increasing. So they're kind of coming to meet each other in some sense. And you can kind of figure out exactly how and when they meet each other so that you guarantee that you're going to lie directly on this kind of updated yield surface during the plastic corrector phase. So that's kind of the simplistic interpretation of what's going on. Ultimately, we want to lie directly on the yield surface if previously we were outside the yield surface during the elastic predictor step. And putting it all together, the whole sequence of steps actually looks, it looks a little bit more complicated because I've broken it up into these kind of like specific sequences of like intermediate computations. But effectively, it really just boils down to compute some kind of trial elastic state of stress based on the old value of frozen plastic strain, but updated total strain. Then go through some procedure that might include some kinematic hardening, evaluate what's the effective stress in the material, that von Mises measure of stress. Maybe also along the way you can compute some intermediate quantities that might be useful for later, things like the flow direction of the plastic stress rate, basically, which is directly just proportional to the apparent sign of this value inside of this absolute value. You can determine what's also the yield stress in the material based on the old value of equivalent plastic strain if you have some kind of isotropic hardening going on. You can then evaluate what's the trial value of this yield function, basically the trial value of the effective stress in the material minus the current trial value of the yield stress in the material. And you can check, is that value for this yield function, is it greater than 0, indicating that we've violated the yield constraint, or is it less than 0, indicating that we still remain within the elastic range? If it happens to be greater than 0, then we have to come up with some new update for what the new increment in equivalent plastic strain should be. And it turns out that, you could just directly use this formula. But in effect, this formula is taken from solving precisely for when exactly does, going down this trajectory meet with kind of like this trajectory of increase in the total yield stress in the material. So it's effectively just solving Fy equals 0 for the corresponding value of plastic strain that satisfies that condition. And that's precisely how you come up with this expression. Then from those values, you can update what's the total equivalent plastic strain in the material, what's the new plastic strain in the material, and finally, what's the updated value of stress in the material given this new updated value of plastic strain. Okay, so not so bad. It's just kind of broken down into a lot of these sub-steps. The other thing that I'll point out, especially if you're trying to implement this algorithm within the context of a finite element code, the other thing you would need is the tangent modulus. Remember the tangent modulus? It told us what's the effective kind of stress strain slope of this diagram. Where now we might have nonlinear material behavior. If we have strictly elastic behavior, then this tangent modulus is nothing more than the elastic modulus, the Young's modulus of the material. But if we happen to have nonlinear material behavior like plasticity, now we have to determine what's this tangent slope of the material during plastic loading. So it'll be different. If we're kind of loading or unloading the material elastically, the tangent modulus will just be E. But if we're loading it plastically in either kind of tension or compression, it doesn't matter. This tangent modulus will be directly proportional to ET, which you can compute in terms of the other parameters, E, and the other kind of hardening parameters as well, as shown here. So it'll be kind of a binary condition whether or not you're kind of doing plastic loading or elastic loading or unloading. Okay. Now, it's interesting, and I'll point out that remarkably, almost like line for line, you can show that the algorithm that I just showed you for the case of uniaxial plasticity actually directly generalizes to the case of multiaxial plasticity. So in effect, if your goal was to try to somehow generalize that same procedure into the context of solving this seemingly much more complicated problem of how do I update, plastic strain and stress now when those quantities are tensors, and how do I do all that now in this kind of multiaxial, stress strain kind of scenario? It turns out effectively the same procedure applies. And the steps are almost identical, one-to-one. Obviously, there's some extra work you have to do because you're working with tensors and, some extra computations that you have to do to that end. And the computation of the tangent modulus certainly becomes more complicated, but remarkably, the overall procedure maintains the same spirit. And to illustrate that, it's useful to kind of examine what's happening in principal stress space as we take these two steps, the elastic predictor step and this kind of plastic corrector step. So supposing we had some kind of view in the pi plane of this kind of principal stress space, and if we had some old state of stress, which we could represent just in terms of the deviatoric state of stress in the material. I'll denote that with an S, with an n-1 to denote the old state of deviatoric stress in the material. And given some increment in strain, we might find that we'll update the total state of deviatoric stress in the material to compute some trial value of deviatoric stress. So the same kind of elastic predictor step that we had before, as in the uniaxial case. And we can also determine, are we within this kind of yield constraint based on the old value of plastic strain in the material? Are we within this kind of cylinder defined in stress space, in which case, we don't have to do anything further. We just have strictly elastic material behavior. Or if we find that we're outside of this cylinder, now we have to figure out a way of kind of returning back such that the state of stress that was outside of this cylinder, somehow we have to get it back onto the yield surface. And there's no better way to go back to return this state of stress back to the yield surface than to proceed along a so-called radial return direction. So if you've gone through the literature and if you've maybe even encountered this terminology before, this algorithm, effectively this elastic predictor, plastic corrector, algorithm is nothing more than what some people refer to as the radial return algorithm. It's a particular form of this, elastic predictor, plastic corrector kind of algorithm, but applied in the multiaxial case. And the intuition behind it is that whenever we go outside of the yield surface, we have to actually update the stress in a direction, which basically returns it along this kind of radial direction relative to the yield surface. That's assuming that the yield surface itself is this nice perfect cylinder, and we can kind of determine this radial return direction as nothing more than basically the normal to this yield surface, which is always outward facing or radially outward. Okay, now you can kind of show exactly how that comes about. How does that influence the apparent rate of change in the total plastic strain in the material? But you can see that if you choose a flow direction that is directly proportional to this normal to the yield surface for how you choose to update the plastic strain, then that too influences a radial return direction for the deviatoric state of stress, which is kind of cool. Okay, so the same basic principle. So if you will understand the one-dimensional uniaxial kind of elastic predictor, plastic corrector concept, then really it's no more complicated in the multi-axial case. It just requires working with tensors and some nasty stuff like that. The one other thing that I'll point out that is particularly nasty when you come to the subject of multi-axial plasticity models is how do you come up with this tangent modulus? Originally, in the case of coming up with simple linear elastic relationships for materials in this kind of multi-axial setting, we had to come up with a tangent modulus for elastic behavior that was this 6x6 matrix array of values that was kind of populated that might involve maybe a dilatational part and a deviatoric part. This is kind of an interesting decomposition of that same 6x6 elastic stiffness tensor that you've seen previously. I've just chosen to break it up in this kind of way, which makes it a little bit easier to express the resulting form for this tangent modulus. Now, obviously, it'll be different depending on whether or not there's plasticity going on, and I've factored that into exactly these expressions. But the other thing that I want to point out about this ensuing expression for the tangent modulus, in the case of a multi-axial plasticity model, applying this same kind of elastic predictor, plastic corrector, radial return concept, unfortunately, even though we had formulated our elastic kind of tangent modulus to always be a nice symmetric 6x6 matrix, unfortunately, in the case of plasticity, we actually lose that symmetric behavior. There's a term in this expression that actually exhibits, a non-symmetric form, which is kind of perplexing. Why exactly does that show up? What's the explanation behind that? Well, ultimately, it has to do with the fact that we've done this update procedure in this kind of two-step fashion. And it's precisely the fact that we've done it in these two distinct steps that contributes to the tangent modulus being non-symmetric in this format. Now, it's worth noting that this particular form for the tangent modulus is sometimes referred to as the algorithmically consistent tangent modulus. It is the tangent modulus that you would get by taking the derivative of the expressions we derived for the stress and taking their derivatives with respect to the current strain increment. Now, that wouldn't be the case if we'd kind of assumed that everything was not done in this incremental fashion and not done in this kind of two-step procedure. So it is something of an artifact in the way that we've chosen to go about algorithmizing this particular, elasto-plastic set of equations. And, in some cases, people say, well, why even bother with this non-symmetric term? Let's just symmetrize it. Take this 6x6 matrix and then just kind of like, sum up each of the diagonal entries and then kind of like average them, basically, so that I get, nonetheless, some kind of expression for the resulting tangent modulus that is symmetric, and therefore I can keep a nice symmetric stiffness matrix. Otherwise, if you keep this non-symmetric form, the stiffness matrix for your problem becomes non-symmetric, which is, introduces a few other challenges, but is nonetheless possible to accommodate. But the whole point of this is, once you introduce these algorithms for trying to update this plastic strain in this fashion, it turns out it introduces some of these other complications. So just be aware that whenever you're dealing with multi-axial plasticity models, this elastic predictor plastic corrector step is nonetheless an approximation as to how we should go about updating the plastic strain. It's not really an exact procedure for how you should do it. It's an approximate way of updating things that is nonetheless rather convenient and intuitive. Okay, so that's as much as I wanted to discuss on this subject of algorithms for plasticity. Now I want to give you an opportunity to try this out for yourselves. So this is precisely what I've given you the opportunity to do in the context of homework assignment number 5, and specifically in problem number 1 of that assignment. So the first, basically this problem number 1, is having you directly implement exactly this uniaxial algorithm as shown through this sequence of steps. So what I want you to do is basically just copy exactly what's shown here. It shouldn't be too hard to do. Implement it directly within the body of some function that I've provided you. I've given you sort of the inputs and the outputs through kind of like the definition of like the function arguments for this particular function of interest. And all you have to do is implement this whole algorithm from start to finish. And at the end, you run a small script to verify, did I do it correctly? And you can run this script to basically visualize what's the stress strain behavior of some material model that I'm suggesting to some history of strain. So basically, the input to this function is kind of like a time variation of strain that might vary as a function of time. And the simplest possible strain history you might consider is simply monotonic loading. Or in other words, take some function of strain that is linearly increasing with respect to time. So it starts at 0 strain and linearly increases that value of strain. And what you should expect to see is something that looks like initially elastic behavior and then subsequently plastic behavior with some kind of characteristic hardening slope. The other ways that you could load the material are simply, cyclically loading the material. So not just monotonically increasing the state of strain, increasing the strain and then decreasing the strain, and then going through multiple cycles of that. So that's exactly how you would get this middle figure. Initially elastic behavior, then loading plastically until eventually when you reverse the direction of the strain, you end up unloading elastically until you load plastically. And you can kind of see that there's combined effects here in this diagram that reflect both kinematic hardening and isotropic hardening. Now, the isotropic hardening component of this diagram is reflected in how the apparent bounds of these kind of like cycles of loading appear to be continuously increasing. As you go through multiple cycles, as kind of like the diameter or bounds of these kind of plastic kind of hysteresis loops become bigger, that is characteristic of isotropic hardening behavior. In contrast, if we had no increase in behavior, but if we still had some kind of slope associated with these diagrams, that would be more characteristic of kinematic hardening behavior. It so happens that both of those things are actually included in this script. So you can kind of like play around with the parameters and see how they differ depending on whether you're using more isotropic versus more kinematic hardening, if that's kind of interest to you. And the last scenario that I kind of suggested maybe taking a look at is this ratcheting scenario, where there are scenarios in which you might load the some piece of material by increasing the amount of strain in it and then kind of backing off just a little bit, going through maybe a small cycle of loading, but then continuing to load it back up to an even larger value of strain and then backing off. And this kind of characteristic loading type of cycle is sometimes called ratcheting behavior. Sometimes it's kind of a problem actually in some engineering design practices where you might exhibit some kind of ratcheting behavior in some structural component, which seems to be elongating continuously over time until eventually you get to the point where you have some component that's like permanently elongated, and it's done so over multiple of these cycles. So that's kind of a problem in some cases. So I encourage you, go try this, implement it. I guarantee it shouldn't be as challenging, I think, if you're just following the steps as shown in the slide. And it should give you at least a little bit better intuition as to what's going on in terms of how these actual kind of stress strain diagrams appear. Okay, now the second problem, of which there's really only 2 problems on this assignment, but the second problem is actually taking that same algorithm that you've implemented in the context of that simple function and plugging it into a proper nonlinear finite element analysis. Now, I've gone through all the steps of implementing exactly that algorithm for you, so you don't have to implement a nonlinear finite element program from scratch. The only thing that you would have had to have implemented is exactly that simple function from problem number 1. So as long as you've done that correctly, you've verified that it's working correctly by running these scripts, now you can go plug it in and run this problem that really just corresponds to a simple uniaxial bar, which is subjected to kind of monotonic extension by some amount applied at the right end of this kind of bar. So the bar starts out initially 0 length, and then it's kind of like stretched to the right-hand side. And I ask you to run this problem for different numbers of elements and for different material behaviors where the elastoplastic behavior of this bar might either exhibit strain hardening behavior, where the slope of this kind of stress strain curve is increasing during plastic loading, or it might exhibit strain softening behavior. That is, it's decreasing as you kind of continue to increase the amount of strain in the material. And what I want you to observe in kind of doing these analyses, running this problem with either of those two kind of material behaviors and with variable numbers of elements, I want you to observe and comment on the potential issues that you see, if you see any, particularly as it pertains to this strain softening. Now, just kind of like to gauge your kind of intuition behind this, do you foresee any issues in running this problem, let's say, with strain hardening behavior? And if so, do you, maybe a better way to phrase this question is, if you were to run this problem and you were to assign strain hardening behavior to this problem, do you think you would get a different answer depending on the number of elements that you use to discretize this bar? Say you used 2 elements or 4 elements or 8 elements, do you think you would get a different answer? I think I see one head no. And then for strain softening behavior, do you think I would get a different answer depending on how many elements I use in this problem? I see one head shaking yes. So intuitively, that's true. You'll get different answers if you're using strain softening and you're using a different number of elements. And to really understand and see that, I encourage you to go through the assignment and kind of see it for yourself, especially if you have some incredulity about that. So go ahead, try it out. And to also give you a little bit more intuition as to what's going on and why this is a potential problem. Why is it a problem that we might have a scenario in which we have just a simple bar and maybe there's nothing that prevents us from doing this, right? Shouldn't we be able to run this problem? Well, imagine trying to do something simple. Not exactly this problem, but one that's kind of like it. Imagine you were going about just running a simple uniaxial stress strain test on some coupon sample or some kind of, dog bone specimen for a sample of steel, let's say, some kind of typical metal or something like that. And you were to go about instrumenting this thing in the usual way. Maybe you attach a strain gauge along the length of the gauge of this kind of specimen, which might have some initial gauge length, L naught. And we can measure the total change in length of this gauge length through some kind of, measurement device. Simple enough. All right. We can also measure what's the total amount of force going through this specimen based on how much load is being applied by kind of our testing machine. And then if we also had some estimate of what's the cross-sectional area of this, gauge length of the specimen, I'll call that A naught, the initial area or cross-sectional area of this specimen before we put any load on it, then we can kind of come up with our standard definition for stress and strain in an engineering setting. So the important thing that I want to distinguish here is that whenever you're running these kinds of tests in a uniaxial stress strain setting, I'm sure you're all aware that we have to distinguish what we mean by stress and strain. And in these cases, really, we mean engineering stress and engineering strain. Engineering strain is really what you might think of as the average strain that occurs over this whole gauge length. It is basically just this total change in length of the gauge length divided by the initial length, which has finite size. And similarly, engineering stress assumes that this cross-section maintains more or less the same size before and after loading, such that we can determine the engineering stress in this kind of cross-section as just the total force applied through the specimen divided by that kind of initial cross-sectional area. So that seems all well and good. And certainly as we go through this kind of loading procedure, as we increase the amount of strain in the specimen and increase the amount of force being put through the test specimen, we see that there's going to be some yielding that occurs along the entire gauge length of the specimen. During this period, we also notice that there's some apparent increase or strain hardening behavior happening in the specimen. So we have a positive tangent modulus associated with this specimen, and more or less, it's reasonable to assume that the behavior along the gauge length is more or less uniform. So if there are plastic strains occurring and accumulating within the material, it's reasonable to assume that they're basically uniform or the same at all interior points along the gauge length. The same thing, we can assume reasonably that the strain, not just the plastic strain, but the actual total strain along the length of the gauge is also uniform and more or less constant along its total length. So that seems well and good up until we get to the point where now the material starts necking. And it localizes within some kind of small subsection of the gauge length. Now, this is where things get a little bit complicated, because as we kind of look at what's the stress acting across this section that has necked somewhat, we have to reconcile the fact that technically speaking, the cross-section of this necked area is actually much lower than the actual original cross-section of this specimen. So really, if we're looking at the engineering stress versus strain relationship in this diagram, it's going to look like the material behavior now exhibits strain softening behavior, right? It's like we had, originally hardening behavior, but now the slope is becoming negative. And is that really reflective of what's happening in the material? Well, the answer is no. In fact, if we were to look at the so-called true stress, which is really the actual force divided by the current cross-sectional area over this kind of next area of the specimen, we would see that technically speaking, the material behavior should continue to exhibit strain hardening behavior. It's not characteristic of most metals to exhibit strictly softening behavior. So really, this branch of softening, as it would appear in a typical kind of like stress strain diagram for one of these kind of uniaxial tensile specimens, really that softening portion of the slope is just characteristic of the necking phase of this whole kind of procedure. It's not really reflective of what's going on in the material. So that's an important point, because if you yourself are going and you're taking some experimental data that somebody has collected, and they give you this stress strain curve, and they call it, here's strain and here's stress, and they don't qualify it. They just say, here's strain and stress, go. Calibrate a material model given this stress strain diagram. You might be very tempted to go and say, well, this material appears to exhibit strain softening behavior. I need to calibrate a material model that kind of includes some behavior such that, past a certain point, I should start to see kind of like the stress strain response with kind of a negative slope. But really, that's just an artifact of the necking behavior. It's not really reflective of what's happening local to the material at some kind of interior point in this specimen. And this is the key point that I want to drive home, which is that really, if you look at different points within this specimen, they are behaving differently. If you look at, let's say, some point directly, at this kind of necked area in the specimen, yes, you will have kind of behavior that kind of looks like this. You should really normalize it by the true stress so that you kind of get this, actual kind of strictly hardening behavior and properly account for the reduction in cross-sectional area of this kind of necked specimen. However, if you were to look elsewhere outside of this necked region, but still within the gauge length of this original test, you'd notice maybe here or here outside of the necked region, you're not loading the material plastically. Locally, this small point of material or this small chunk of material, they're actually unloading elastically. So it's not like you're uniformly loading this whole section of the gauge length of this specimen uniformly in plasticity. The strains are localizing. They're kind of becoming larger and larger in this kind of area where the specimen is necking. And that is really difficult to assess if you yourself have not run the experiment and if you're not aware of whether or not this kind of phenomena is occurring. Which basically means that if you're working with stress strain data that somebody has provided you, and you don't have a lot of those insights, you might make the mistake of saying, I'm just going to calibrate a material model that, exhibits strain hardening behavior up to a point and then exhibits strain softening behavior. But that's very dangerous. In general, if you're calibrating, especially models for metals, you kind of want to make sure that the actual material calibration is always exhibiting strain hardening behavior, not strain softening. Because, again, you could make the mistake of conflating nonlinear material behavior for what is effectively a nonlinear geometric effect. And we'll have to dive into that subject in next lecture as we kind of start to discuss and move away from material nonlinearity and instead start discussing geometric nonlinearities. As we'll see, really necking behavior is something of a combination of both material nonlinearity and geometric nonlinearity happening at the same time. Really, you can evidence why is this a geometrically nonlinear phenomenon by virtue of the fact that we had to normalize this kind of measure of stress by the actual deformed area of the specimen. So we had to take those kind of like deformed geometric features into account when we actually define what do we mean by stress and what do we mean by strain. So we'll have to review and revisit some of those topics next time, but otherwise, feel free to visit me in office hours if you have follow-up questions or questions pertaining to the homework assignment. Otherwise, best of luck.